Before getting into complex numbers, let's look at imaginary numbers, like 7i and 2i. If you add them together, what do you get? Right, so 7i plus 2i is 9i. Now, instead of adding two imaginary numbers together, let's add a real number like 3 to the imaginary number 2i. There's no way to further simplify this expression, right? So we have a real number plus an imaginary number. And this is what's known as a complex number. It's any number that can be written in the form a plus bi. So that's a real number plus an imaginary number. Let's look at a few more examples of complex numbers. 4 minus 5i, which you can also write as 4 plus negative 5i. It's a real number, 4, plus an imaginary number, negative 5i. Another example is the real number 4 by itself. But wait a second, what about adding an imaginary number? Well, we can equivalently write this as 4 plus 0i, right? So for this complex number, a is 4 and b just happens to be 0. So all real numbers are also complex numbers where the coefficient of the I term is 0. And 5i by itself is another complex number. It's the same thing as 0 plus 5i. So imaginary numbers are complex numbers where the real term is 0. So next, which of the following are complex numbers? For which of these can you find values of a and b and write them as a plus bi? Exactly, they're all complex numbers. 17 is 17 plus 0i. This is 0 minus 8i. And 0 is the same as 0 plus 0i. So all of these are in fact complex numbers. Next, let's take a closer look at the complex number negative 6 plus 3i. When you see notation like this, a complex number in parentheses with re written outside of it, that means we're taking the real part of the complex number. So what's the real part of negative 6 plus 3i? It's negative 6. That's the part that's real. Try finding the real parts of a few more complex numbers and keep in mind that the real part could be 0. Right, so the real part of 2i plus 7 is 7. Negative 5.3 is already a real number, so its real part is negative 5.3. And 8.6i is an imaginary number, so its real part is 0. Okay, so that's the real part of a complex number. When you write a complex number as a plus bi, the real part is a. Similarly, the imaginary part, or the im of the complex number, is b. So the imaginary part of negative 6 plus 3i is 3. Notice that it's not 3i. It's just the coefficient of the I term, the number 3 by itself. So go ahead and find the imaginary parts of the three complex numbers you saw earlier. Excellent. The imaginary part of 2i plus 7 is 2, because that's the coefficient of the imaginary unit. Negative 5.3 is real, so its imaginary part is 0. And the imaginary part of 8.6i is 8.6. Try a little more practice and find these imaginary parts. Right, so this first imaginary part is negative 4. 7 plus I is the same as 7 plus 1i, so this imaginary part is 1, and the imaginary part of 7 minus I is negative 1. Before we dive into the complex plane, go ahead and find the real and imaginary parts of these complex numbers here. Now, it turns out you can plot complex numbers just like you plot xy coordinates on the coordinate plane. So this is called the complex plane. but instead of x and y axes, it has a horizontal real axis and a vertical imaginary axis. So if you wanted to plot the complex number 1 plus 2i, its real part is 1 and its imaginary part is 2. So this is the point 1 plus 2i on the complex plane. Try selecting the point that represents the complex number 4 minus 3i. Nicely done. So 4 minus 3i is this point over here, with a real part of 4 and an imaginary part of negative 3. Next, what complex number would you say this point here represents? Nicely done. Now, just like the coordinate plane, the complex plane has 4 quadrants. Quadrant 1 is over here with positive real and imaginary parts. Quadrant 2 is over here, Quadrant 3 is down here, and Quadrant 4 is over here. Okay, so go ahead and select any point in Quadrant 3 of the complex plane. Excellent! And of the complex numbers listed here, which is in Quadrant 2? Right, so negative 3 plus 2i, which has a negative real part and a positive imaginary part, is in Quadrant 2. As you'll see in a later lesson, the complex plane comes in really handy when multiplying complex numbers using what's called polar form. And the complex plane is also related to many fractals, like the Mandelbrot set shown here. You might have seen the Mandelbrot set before, which has this peculiar shape. But notice also that the set is plotted on the complex plane, with real and imaginary axes. All the complex numbers shaded black in this image, like 0 plus 0i, negative 1 plus 0i, and negative 1/3 plus 1/3 I, they're all part of the Mandelbrot set, which you can learn about in a later lesson.